PowerPoint presentations, no, dalawa. I haven't sent you those because I thought uh, since I have this wasn't discussed with you in your ARC 171, so I better discuss it now because this is important. These are important concepts so that you can better appreciate yung mga susunod pa nating i-discuss like yung three-moment equation method. Okay, so the the title of this presentation is it is about the concept of determinate and indeterminate structures. What are unstable systems? Then how to determine the degree of static indeterminacy, whether external or internal. What do we mean by statically determinate and indeterminate? It says if the number of independent static equilibrium equations is not sufficient for solving for all the external and internal forces, that would mean the support reactions and the member forces respectively in a system, then the system is said to be statically indeterminate. Okay? It says here independent static equilibrium equations. So usually we have three, no? Summation of forces along the x-axis. We're talking about two-dimensional systems. And then summation of forces along the y direction. And then summation of moment at any point. No? So, tatlo yon usually. No? So, if the unknowns exceeds 3, then uh, the equations, no, the available equations wouldn't be sufficient so that we'll be able to get the external and the internal forces. Of course, why do we need to determine the internal forces? So that you can appropriately design the member. No? Malalaman mo kung gaano kalaki dapat. At least yung preliminary dimensions. Okay? Like what we have been doing, no? Yung when we designed the beam, the slab, okay? We generate the shear and moment diagrams. Okay, but there are cases that it's the system is not that simple. No? It gets complicated. Like there are what we call redundant forces. Now, what about a statically determinate system? It is that case when all the support reactions and internal member forces can be obtained using only the static equilibrium equations. Those are statically determinate. When the three equations, available equations, are just enough to come up, with the reaction and internal member forces, then it is statically determinate. Okay. Now let's have some illustration, no? Kung ano yung statically determinate structure. These are statically determinate structures. Okay? You have a pin support here and a roller. Okay, and then you have concentrated load, a moment, and then a uniformly distributed load. Now, the reactions here would be, okay, you have a vertical reaction and a horizontal reaction. Oops. Okay. Would there be a moment reaction here? If it is a pin supported reaction. So ito, if it is a pin supported, then it is free to rotate. So kapag free to rotate siya, it doesn't resist any moment force. Okay, the support here. So kaya ito lang yung magiging reactions niya. It prevents this beam from translating along this direction and along this direction. Okay, what about in here? It's only vertical yung restraint. Okay? Vertical lang yung restraint natin dito. So, our beam cannot translate in this direction. Of course, if this is a roller, it can translate upward, no? But all of the forces are going down. So, the only possible happening here would be this to go down, supposedly because yun nga ang forces niya pababa. But since you have a support here, hindi na siya magta-translate in the vertical direction. And also, uh, pin roller, so it doesn't resist any moment at this point. Okay? Now, this frame is cantilevered, no, or fixed support. Or if it is fixed support, you have a vertical restraint, horizontal restraint, and a moment restraint. Okay? May moment restraint ka rin dito. Mali yung ano ko. I have to change my... How do I change that? Anyway, that's a moment restraint, no? Format. Okay, that's it. Ito. Okay? Moment yun. So, moment. Ito, B, H. Okay? So, those are the restraint, no, at this support. Now, the third one is a truss. So it's been connected here and a roller here. Okay, of course, you know already when we're talking about trusses, no? For trusses, idealized yung situation. No? How is it idealized? All of your members in here are actually loaded. They are assumed to be actually loaded. And along with that, assumptions also would be the connections here, okay, the nodes are frictionless. No? So if they are frictionless, so there won't be any moment, no? The restraint at the nodes. Okay? Now, again, reactions natin would be here. Restraint mo doon. This is vertical here. Okay, those are the reactions. So, notice that reactions, we have three. 1, 2, and 3. So, 1, 2, and 3 because you only have 3 available equations. No? Those are the equations I mentioned earlier. Dito rin, no? Okay, vertical, horizontal, and the moment. Okay? Now, what about statically indeterminate? Now, statically indeterminate, the difference between the previous slide, merong konting pagbabago. No? Originally, this support in here is a roller. Now you have a pin. So if you have a pin, madadagdagan yung restraint. No? If that is a pin, instead na going up lang yung restraint mo, meron ka rin horizontal dito. Horizontal restraint, horizontal, and then vertical. Yeah, so instead of 3, you have 4. That makes it indeterminate. Okay, kasi sumobra na yung yung unknowns mo versus your available equations. Okay, what about this one? So in here you have three, one, two, and then three. But then you have a pin support here. So madadagdagan pa dito. I have here one, then two. Yeah? So instead of tatlo lang, naging lima yung unknowns natin. Okay? Now, what about this one? Pareho pa rin. Okay? You have the same support reactions. There. Okay, from the original, from the previous slide, you don't have these member forces. Ito. Tsaka ito. No? So, nadagdagan yung member forces natin. So, you have redundant members. One and two redundant members. Okay? So, uh, based on the redundant members or redundant reactions, redundant supports, okay, we can tell whether it is internal or external. No? If it is a redundant support, then it is external. So what is the redundant support here? This one, then this one, and this one. Tapos ito, at saka ito. So itong this one is external. These two are external, and then these two are internal. Okay? You see the difference whether it is internal or external. If the redundancy is in the support, then it is external. Then if it is in the structure itself, it is internal. Okay, you got that? Sige. Good. It says, for an indeterminate system, some supports or internal members can be removed without disturbing its equilibrium. These additional supports and members are known as redundants. So, these are yung mga redundants, mga additional support yan. Then it becomes an indeterminate system. Okay, why do you think in most cases there are redundant supports or redundant members? Sa palagay niyo, why? In your opinion, why? Any guess? Okay, for safety, no? For safety reason, because if one member fails, then your system will still be stable. Okay? In case of a redundant support, when one support fails, stable pa rin yung ano mo, yung structure mo. Of course, nasa pag-aaral yan ng structural engineer with the geotechnical engineer. Who knows what a geotechnical engineer does now? Kung ano yung ginagawa ba ng geotechnical engineer? Anyone? Hesitation. Yung structural engineer, very familiar kayo. What about a geotechnical engineer? Geotech. Miss Daniela, you know any? Tatawag ako Check ko lang kung familiar kayo.
Hello, sir.
Yes,
Hindi pa ako familiar, pero
that's such a
nag-search po
technical.
ako.
It's okay. It's okay.
Nakalagay po dito na part po siya ng civil engineering pero mas focus po sa behavior ng earth material. So, I'm assuming po na more on ano po siya, dun po sa mga foundation, like
Yes,
dun po sa mismong land,
correct.
nakafocus.
Correct. Tama yan. The geotechnical engineer, he takes care of the design of the foundation. But what he does, he studies muna yung soil underneath your structure. So perhaps I will do a penetrometer testing. Nakuha sila ng soil sample, not just dun sa surface, but also yung sa baba, lalo na kung mabigat yung structure natin. It's because it's the soil who will that will bear the weight of the building. Tama? So yun ang geotechnical engineer. Okay. The terminate system has the exact number of supports and internal members that it needs to maintain the equilibrium and no redundance. Okay, kapag determinate ang system natin, wala tayong redundance. When one member or one support fails, then unstable ng system natin. Okay? So, of course, architects and engineers wouldn't want that, no? Yung madaling mag-fail yung structure. It says if a system has less than required number of supports and internal members to maintain equilibrium, then it is considered unstable. Okay? The two-dimensional prop cantilever system in the figure is an indeterminate system because it possesses one support more than that are necessary to maintain its equilibrium. If we remove the roller at the end B, it still maintains equilibrium. At this point, the number of unknown support reactions has the same number of independent static equilibrium equations. So it says this is a propelled cantilever AB. So it's cantilevered here, fixed support, and then you have a roller. Actually, this roller is a redundant support. Now, if we remove that support, then it becomes like this. You have a vertical reaction, horizontal, and a moment reaction. Still, it is stable. Okay? FBD of cantilever AB with no support at B. Cantilever AB with no support has these equations. No? Ito yung mga reactions niya. And then these are the available equations of static equilibrium. Summation of forces along the horizontal. Pag x horizontal yan, of course, yung forces along y, vertical. And then summation of moment at any point. Zero lahat. From the very start, we always equate that to zero. Why? Why do we equate all of those to zero? Because we have a stationary structure. Hindi yan gumagalaw. It's not dynamic. Na-encounter nyo yung mga static equations of static equilibrium in static of rigid bodies. No? Yeah, static siya. That's why we equate to zero because acceleration is equal to zero since velocity is equal to zero. So it's not accelerating. Therefore, the net force and the net moment. No? In translational and rotational all equate to zero. Okay? Now, how do we solve for the indeterminacy? Okay? It's degree of static indeterminacy, that is total number of unknown external and internal forces minus the number of independent equations of equilibrium. Let's say for a truss system, you have a total number of unknown forces, the number of members, plus the number of support reactions. No? Then the total number of independent equilibrium equations, you have 2 times n is the number of nodes. Now this is based on the method of joints. No? If you use method of joint, you only take on summation forces along x and then summation of along forces along y, then you should be able to get the member forces of each element in the truss. No? Therefore, degree of static indeterminacy would be m number of members plus number of support reactions minus 2 times the number of nodes. Okay. Now for illustration, we have this. No? Now, it says here determinacy, indeterminacy of a few two-dimensional pin-jointed truss systems. So this is, take note, two-dimensional tayo. Ano? Okay, M is 17. Bibilangin lang yung mga members. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so that's how we got the M, number of members. No? And you have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then R, you have 1, 2, and then 3. Okay, did you get that? Okay, let me draw that. 1, 2, 3. Okay, that's why this is 3. Yeah. So in here it says degree of static indeterminacy is equal to 0. Therefore, the system is statically determinate. So let me show that how we computed for that. So m plus r minus 2n. Okay, so that's equal to 17 plus 3 minus 2 times 10. So that's equal to 0. Okay? Any question? Nagets natin yan? Now, what about the next one here? So if you will compare this, the truss here, so let's compute for that. M, so member, nadagdagan ng isa, no? Instead of this only, there's an additional member here. So M would be 18. 18 plus 3, okay, minus 2 times 10. So that's equal to 1. Okay? Now, you see here, since meron tayong, we have the answer here to be 1, we say that's internal yung static indeterminacy siya because the redundant member is, within the structure itself. In this case, the truss. Na? Now, the third one, you have the same truss, okay, but you have an additional support in here. So instead of only having three supports, you have four supports. No? So you'll have here 17 plus 4, okay, minus 2 times 10. So this is equal to 1. So, and therefore, we have an excess of 1. No? So that's the measure of the static indeterminacy. This time it's external, okay? It's externally statically indeterminate because the excess is in the support. Okay? Any question? Okay naman? You got it? Any question? Sige. Okay. Now, if you don't have any question doon, we proceed right away to the concept of symmetry and antisymmetry. See, so we'll talk about the two relatives. No? Yung isa anti niya. So that's why it's antisymmetry. Okay? Pero how are they related? So we'll study symmetry, asymmetry, and antisymmetry in structures. Symmetry and antisymmetry in equilibrium and compatibility conditions. And then the use of symmetry and antisymmetry in analyzing a structure. Okay? Symmetry or antisymmetry in a structural system can be effectively exploited for the purpose of analyzing structural system. Okay, when you say exploited, hindi naman yung nang-aapi ka. Na? Hindi, you're using it to your advantage. Na? Okay, symmetry and antisymmetry can be found in many real-life structural systems or in the idealized model of a real-life structural system. Later on, you will see when we discuss portal method and cantilever method, we take advantage of this. No? Yung, idealize, when we idealize. Pag may mga assumptions tayo no? Based on observable phenomenon. Okay? It is important to remember that when we say symmetry in a structural system, it implies the existence of symmetry both in the structure itself, including the support conditions, and also in the loading on that structure. We illustrate symmetrical structural systems. So look at this one. You have a beam supported by pin connections at both ends. Okay. You see here EI. What is E? Palagay nyo, what is E? That's not my initial. Huh? That's it pertains to another. It's actually the property of the beam. No? Modulus of elasticity. Correct. Parang may narinig ako sa inyo sabi. Then what about I? Ano yung I? I? Anyone? Reina.
So, moment po siya.
Ano yan?
Moment.
Sorry?
Moment.
Hazel. What is I? Okay, in our last lecture on deflections, we were computing for I, di ba? When we were computing for the deflections. What is I?
Sir, moment of inertia po.
Correct, correct. Moment of inertia. Okay, so E is modulus of elasticity. Okay, constant ito, no? Based on the property of the material used for the used on the beam. No? Yung I naman is a sectional property. So the value of I depends on the dimensions base and height. No? The moment of inertia of a rectangular section at its not at its base, no? At its center of gravity is BH cubed over 12. Diba? Now, take note, yung H doon is cube. No? So, what influences the deflection of a beam? Ano yung mas nakaka-influence doon sa moment of inertia ng beam? Because of that equation, you can tell na yung H. Na? Paglalakyan mo yung H, cubic ang increase ng moment of inertia niya. No? So, very important yung height in controlling for the moment of inertia. And moment of inertia, okay, influences the flexural stress. Yung formula na MC over I, that's the flexural stress, no? Maximum flexural stress. If you increase the I, then the flexural stress decreases. No? Maximum flexural stress. Okay? And of course, the base then is, or the base also influences the moment of inertia. Okay, so this one is basing it on sa property ng material E and I. It's uniform from this point up to that point. So left and right side, you could say they're mirror image, no? Not just the geometry, but also the material. Okay, ito rin. Even if the supports are a little bit moved from the end, it goes to the left. This one is located here. Okay, still they are symmetrical on the left and on the right. Okay, for this one also, you have fixed support at the left end and fixed support on the right end. Now, what about the moment of inertia? Moment of inertia, in here, it becomes 2I. Dito I lang. You can see na that there's a change in the sectional property. No, yung measurement ng height, it changed. No? But then, if you compare the left part and the right part of the beam, parehong sila, mirror image sila. For this one also. Okay, so it should be loading. Yung loading nila, yung red arrows, no, those are the loadings. They should also be symmetrical. And also the section and support. So yun ang titignan mo. No? And for this one also, okay, E and I are uniform from left to end. And also the loading. No? Loading starts from the end going to the center. Okay, ito naman from the center, pareho siya to the left and right. Now, what about non-symmetrical? Look at this one. The beam is symmetrical, and the loading pareho rin, but the supports are not. No? Dito pin connected. This is fixed. Okay. Then for this one, which is not symmetrical, the loading. No? Although the loadings are equal in magnitude, but they are not acting at uh, at a symmetrical location or at a point where uh, your system wouldn't be symmetrical, or in practical terms, they won't be mirror image. What about this one, which is not symmetrical? Supports are symmetrical. Okay, this beam is symmetrical, or for this case, we call it a column. No? But for these two beams, the sectional property is not symmetrical. Ito I siya, ito 2I. So hindi siya symmetrical. So non-symmetrical to. Okay? So we have symmetrical and then non-symmetrical. But we have anti-symmetric. Okay, anti-symmetric. You can see naman right away kung anong ibig sabihin ng anti-symmetric. No? For this one, symmetric yung geometry. Okay, your section, E and I are symmetrical. Your supports are symmetrical. But your loadings are anti-symmetric. We call it anti-symmetric. They are acting at a point na symmetric but in opposite direction. Okay, so you call this, or you describe you identify this as anti-symmetric. Okay, for this one also, the supports are symmetric. The E and the I's are symmetric, but the loadings are not. But we say they are anti-symmetric. Same what do you call this? Same magnitude, but opposite in direction, and acting at a symmetric location. Okay, kasi ito L over 6, L over 6 to. So pareho yung magnitude nila, but they are different in direction. Okay, there are implications in this kind of structural system, no? Yung mga anti-symmetric. Okay, and then this one, they're symmetric in E and I, supports symmetric then. But then, doon sa loading nila, they are anti-symmetric. So these are anti-symmetric structural systems. Okay, nagets natin yan? Do you know the difference now between symmetrical, non-symmetrical, and then anti-symmetrical structural system? Okay? Mr. Basilio, you have any question? DJ? Question?
Gets naman po, sir.
Okay naman. Good.
Opo.
Sige. Now, we look at the deformation in symmetric systems. So look at this. If this is symmetric, this is a symmetric system, and the deflections, you'll see they are also symmetric. Okay, symmetric then yung deformation. Yeah. This one here, by the way, let me just mention this para makabisado ninyo. Okay. May chat dito. Moment of inertia. Yeah. Chinat nyo pala. Hindi ko kagad nakita. Alright. Let me annotate this. I just would like to mention that. You see this at this point here, merong rotation yung beam natin. Okay, I hope you understand when I say there's rotation. If you draw a tangent line at this point, tangent line yan, no? At this point of this curve, then it makes an angle, no? From the horizontal, okay? Because it is pin connected at these points. That's why merong ano yan, merong angle, no? But then this one, since nako-compensate yung rotation niya on the left side and the right side, the uh, the slope here is 0. Okay, but then this one here has also rotated. Okay, now if it is fixed support, horizontal yung tangent line to this curve at this point. Okay, I hope you see the difference. No? Ito, tsaka ito. Yeah, because as we mentioned earlier, wala tayong restraint ng moment dito. Dito meron. Because for fixed support, the angle here is maintained. No? It's maintained to be perpendicular to the support. No? Itong axis ng support natin, which is vertical. So this one is horizontal. Okay, same is true with the other end of the beam because it is fixed supported. Okay, so symmetrical din yan. This one also is symmetrical. And then this is symmetrical. Yeah. So you'll notice if you have a symmetrical system, your deformation should also be symmetrical. Now, for antisymmetric system, this is the deformation. So deformation basically is also antisymmetric. Okay. For this beam, you have this. No? Notice, I just want to mention this. Yung degree of deformation here and deformation there, let's say the amplitude, no? They're just the same, but different in direction. Okay? Ganun din dito. Deformation here, deformation there. Okay? Equal lang mga yan. And here, and there, and then dito, and there. Okay? So we call this antisymmetric. They're almost symmetric, pero anong pinagkaiba nito? Iba yung directions nila. No? Okay. So the use of symmetry and antisymmetry in analyzing a structure. Beam AB is symmetric about point C. The deformed shape of the structure will be symmetric as well. Okay, like what we observed in the previous slide. Therefore, if we solve for the forces and deformations in part AC of the beam, we don't need to solve for part CB separately. Okay, the symmetry in deformation gives us additional information prior to analyzing the structure, and this is information can be used to reduce the size of the structure that needs to be considered for analysis. Actually, we did this already, no? Doon sa computations of the spacings of stirrups. No? If we see that the shear in the shear diagram, if it is in that case we have antisymmetry, no? See in the shear diagram. Pareho yung magnitude sa left and right, nga lang yung sign nila magkaiba. But when we analyze them, no, ang makukuha mong spacing, pareho pa rin. because we only consider the amplitude of the shear forces. Okay. It says if we want to reduce the symmetric beam in the previous slide to its one symmetric half AC, we have to integrate the fact the slope at point C for the reduced system AC will have to be 0. Now, this will be a necessary boundary condition for the reduced system AC. So if we want to represent uh, the system on the left side, because you have a 0 slope at this point, then therefore your system will be something like this. No? You have a shear release in here. So meron kang uh, shear force at this point. No? But you should have a 0 slope at C. Okay? Meron kang you have to represent that, no? Now that's why you will have a roller as a representation of that, so that your beam will have or will not rotate in here, no, when it reaches the maximum deflection. Okay, we can achieve this sorry by providing a support at C, which restricts any rotation but allows vertical displacement, as shown in Figure 1.21. So everything else remains unchanged in the reduced system. We can use the system AC for our analysis instead of the whole beam. So the left side lang ang i-analyze mo. Okay? Antisymmetric simply supported beam. So this is the antisymmetric simply supported beam. The deformation would be this. No? So you will have a displacement equal to 0 at this point. So therefore, this system can be reduced to this system. Being connected here, only half of the beam will be considered. Okay. Then you will have a roller in here so that it can facilitate rotation. Okay, but you will have the 0 displacement. When you say 0 displacement at C, that's the vertical displacement. Okay. So if you are analyzing, or let's say the structural engineer is analyzing many structural elements, let's say 50 kamo na. But since most of them are symmetric or antisymmetric, reduce into 25 na lang. No? Because you can have this assumption. Okay. Now, having a prior knowledge about symmetry and antisymmetry and its deformed shape help us know about symmetry, antisymmetry in internal forces in that system. Internal forces in a symmetric system are also symmetric about the same axis, and similarly, antisymmetric systems have antisymmetric internal forces. Once we know about these diagrams, we can easily see the following. Okay, it says here, a symmetric beam column system has a symmetric bending moment diagram. Okay, symmetric then yung bending moment diagram. And then a symmetric beam column system has an antisymmetric shear force diagram. Okay. Then it says here, an antisymmetric beam column system has an antisymmetric bending moment diagram. An antisymmetric beam column system has a symmetric shear force diagram. Now, if you want to have a pattern for this guidelines, yung bending moment diagram, it always follows whether it is symmetric or antisymmetric beam column system. Okay? Kung symmetric yung bending moment diagram. The shear force will always be the opposite. No? If you have a symmetric system, beam column system, antisymmetric yung shear force. No? Now, if it is antisymmetric, then your shear force diagram would be symmetric. Okay? Nagets natin yan? It's not easy to follow, no? It's not that difficult, no? Yung beam diagram, it always follows, no? Symmetric din yung beam diagram. Antisymmetric din yung beam diagram. Yung opposite is always the shear force diagram. Pag symmetric, antisymmetric yung shear force diagram mo. Pag antisymmetric, symmetric yung shear force diagram. Yeah? Nagets natin? Okay, this is how it is. So look at this one. This is symmetric. For symmetric, your bending moment diagram is also symmetric. But the shear force diagram is antisymmetric. So as we said, opposite palagi yung shear force diagram. Pareho yung bending moment diagram. Now we have here antisymmetric. You have antisymmetric bending moment diagram, but you have symmetric shear force diagram. Okay, do you get the pattern? Nagets nyo? Okay. Now you have a sit work. Okay, so what time is it? I'll give you 10 minutes for this one. Yeah. Kaya ganito na lang. You just screen capture. So at this point, screen capture nyo muna. And then just submit to me at the within the day. Madali lang naman to. It's very easy. Okay, and then we take a break for a while. Let's have a 10-minute break. Okay, docs. Sige, screenshot nyo na. And then give me a thumb up sign if you have screenshot it already. Yan, good. Mga sanay mag-screenshot. Yep. Yun eh. So, close this na. Stop share. Okay, 10-minute break. Let's resume 10:17. It's 10:07 now. 10:17 tayo resume.